more esoteric stuff. So what I want to do is kind of fly over some of the more esoteric stuff so you know that it's there, kind of how it looks and feels, so that if you reach the point where you need it, you have a landmark in your head. It's not important so much that you actually have done it, it's that you know how to find information about it, for instance, on the internet, or how to look through this documentation and find more information about it. So we have an hour left. That's correct. So I'm basically going to move at kind of the pace we started the class in. But so if you have questions as we go, just raise your hands, but I'm not going to stop and have people do the exercises. Does that sound okay? Okay, good. Right, so inheritance, Boost Python allows you to specify inheritance so if I expose one C++ class in Python, I can say that this is also a subclass of some other class that I've exposed. So if I have, it's very simple. The syntax is, it's this class underscore, the same template we've seen already, with the class you want to expose, and you're telling Boost Python that this has some base classes, some C++ base classes, and so you use this is a Boost Python bases template that you pass to it. So if you remember, we had this entity struct that we defined earlier, as well as the matrix class that we defined. Now we're saying that matrix is an entity. For whatever reason, don't question the logic. So now, when I expose entity, I do that in exactly the same way that we've done before. It's a standard class exposure. But I want to tell Boost Python that matrix is a subclass of entity, and that's how I do it right there. What this will do, we'll see how it's now when I use this in Python code, I can construct a matrix using its constructors, just like we've told it how to do. But I can see that the matrix has an ID and a name attribute. And it got those because I told Boost Python that matrix has all the stuff that comes from entity, and we've told it how to expose entity. So it knows in Python that it has ID and name. It's cool that this works. It means that you can very naturally expose inheritance hierarchies, class hierarchies from C++ into Python. And it's as simple as it looks right here. Oh, sorry, I didn't mean to go forward like that. It's pretty clear. The only thing we're adding is this bases argument, template argument, to the class underscore template. Right. So, okay, this is the to-do. Don't worry about it, but if you wanted to, you can do this later. Enums, of course, Python doesn't have any notion of an enum built into it. It's just not a native element of the language. But C++ does, and so Boost Python wants to provide a way for you to access your C++ enums in a natural way in a Python environment. So if you had to guess how to expose it, you'd probably be right. It's something called Boost Python enum underscore. Really straightforward. If I have some enum here with a couple of different kinds of projections, Mercator, Demaxian, sinusoidal, I expose those in my Boost Python module definition using Boost Python enum. The template argument to the enum underscore type is projection. That is the name of the enum that I want to expose. And the function argument is the Python name that I want to give it. And then for each value in the enum, you call .value, you give it a Python name, and you give it the C++ enum value name that you want it to map to. Essentially, this constructs a Python object, a Python class that has a couple of read-only parameters on it. So you can kind of see how this looks. It's actually a very high-powered class in many ways. It's more powerful than a C++ enum because it's introspectable. So now if I import this enums module that I just created above, I can see that there's a class called enums.projection, which is this. That's what I told it to call it right here. I can ask the projections class for all of the names of the elements on it, all the names of the enum entries on it, and it will print out this dictionary, which maps from name to value. Yeah, you can see that they have, holy moly, not printing anything. The enum values in Python have integer values that can be compared to other integers. It's nothing complex going on. It's pretty much as straightforward as you can imagine the mapping would be. So if you need enums, remember enum underscore. This kind of goes back to some people were talking about how to expose certain functions that used enums, and this is how you do it. If you have enums that need to pass back and forth across the language barrier, use enum, and it just works. That's if you want to try it. Derived object types. So way early in the discussion, we talked about protocols. And we know we have these things like list and dict and tuple that all sort of follow some protocols. Really, they're the canonical instance of certain protocols. List is the instance of list-like things. Same with dict and tuple. Very often, it's useful to be able to pass actual Python lists into C++. You have some list of values, whatever. You don't want to copy it into some kind of vector or anything other thing. You just want to give the list to your, C++ module. So Boost Python has a number of wrapper classes, really, with Boost Python object subclasses that help you handle this very seamlessly. And the important ones, the ones we'll kind of look at, are list, dict, and tuple. So imagine that we've got some function called expensive computation that does some expensive computation. And we want to run some calculation that involves that expensive computation over a bunch of Boost Python values. So we have a C++ module for the sake of having this expensive computation, because that's what C++ is good at. But we want to be able to pass a large list of Python objects or Python values down to it. So the short explanation of how to do it is you use the Boost Python list class, and you can work with it very much like a list in C++. It has functions like len. Well, there's bplen, Boost Python len, which can work on values on lists and tell you the length as an integer. You can extract, well, you can use square brackets on list objects to get the Boost Python objects at those indices, and it will throw the proper exceptions if you do the wrong thing, if you index out of bounds, for example. Extract, of course, just pulls the integer values out of the list. The point here is that Boost Python has a couple of handy convenience classes that wrap around the functionalities of lists, dicts, and tuples, and you can pass them very easily across the boundary. And the APIs for the list, dict, and tuple are exactly what you would expect if you're used to using them in Python. So that's the point. And this is great because you can avoid copying things if you have large chunks of data stored in these data structures. Yeah. Mm-hmm. And I have to make a value copy. I see what you're saying. Yes, it should do the right thing because all of its interaction with the Python object is looking things up by name and then calling them. So there's no hard links. It's all super dynamic. Yeah. And even if you have something that's not actually a subclass of list at all, but just has all the right functions, or has enough of the functions to fulfill what the calls you make, it'll still work. So duck typing is actually going on in C++ land here. Yeah, more examples of how that works. Yeah, there's plenty of documentation on these. These things are actually pretty well documented in the Boost Python documentation. And you can play with it if you want. By the way, if you look in the workshop material, there's a directory called answers, and it has basically answers to all of the triads in the slides. So if you want to see how these things all work, you have all the final solutions in your code, in your repositories. Right, so we looked at properties earlier, and you can also directly expose, and properties, of course, are functionally backed values in Python land. But you can also expose C++ data members directly if you want. And the way to do that is with this pair of functions, def read only and def read write. These are simply members on the class object that was returned from class underscore. So here you can see if I want to expose ID directly, say it was a public data member on entity, I can just use def read only with the name and the address of the thing I'm exposing, the integer in this case. And I can do def read write for something like name, which I feel like I can read write to. I mean, this of course this treads on a lot of people's toes. They don't like having exposed data members like this. So maybe you never run into this, but it's there if you need it. And if you have structs that you're working with, very often they have publicly exposed data members. Yes? Oh, like ampersand entity : ID? Well, the type of that is technically const int, but that's a pointer to a member variable. That's what that is. Yeah, all that is the address of ID inside a class. Yeah. And exposing it works just like you might expect. I'm not going to go into details here. But if you, okay, this is saying that if you try to write to a read-only attribute or a read-only data member, you get an attribute error, which is probably what you'd anticipate if you work with Python. Skip that. Skip that. All right, type conversion. This is a topic that's come up a couple of times. This type conversion ultimately is how can you set up bits of code that can take a C++ object and convert it into a Python object so that it can transfer across the boundary. So if you created your own user-defined class or type, which of course most of you are going to do, and you want to be able to take it from C++ and pass it into Python, this is how you do it. This is not a simple topic. It's a bit involved, but I'll try to go through it at a slow enough pace and at a high enough level that you at least get a sense for what the moving parts are. There's really only sort of 3 moving parts. I call them moving parts. They're just bits. But you'll get a sense of how it's all put together so that if the time comes when you need to do this, of course, you'll know how to do this. There's some good blog posts on the internet about how to do this. Documentation in Boost Python itself is not all that good. So it's useful to think about when is type conversion necessary. And there's really only 2 times when it's necessary. One is when I'm constructing a Boost Python object. So I'm in C++, and I have some C++ object that I want to construct a Boost Python object around. When I construct that Boost Python object at runtime, Boost Python is going to want to make the conversion from C++ to Python. So it invokes the machinery to convert to Python. The other time is when I use extract, and extract is going the opposite direction. I've got some Python object, and I want to convert it into C++. And so I say extract to this type from this object. Those are the only 2 times, as far as I know, and I'm fairly certain about this, that the conversion routines are invoked from sort of user-level code. So to create a converter, a complete converter to and from Python, you need 3 things. You have to define a function that takes your C++ thing and spits out a Python object. You need to have a function that checks if a Python object can be converted to some C++ type, and you need a function that can convert from that Python object to your C++ type. So sort of three things that have to get done. And these functions have to be registered with the Boost Python runtime as well. So there's some set of tables and stuff like that using type IDs and RTTI and things like that to make all of this magic happen. So for this example, we'll have this simple little coordinate class. It's a struct with an x and a y, about as dirt simple as you can get, and we'll see how to expose that into, or how to write a custom converter to take that back and forth across the language boundary. So what we're going to do is take the C++ coordinate object, and we're going to convert it into a Python tuple to take it across the boundary. So coordinate goes from being a C++ thing into a Python tuple when it goes through the conversion process. So what's the first function we need to write is the one that takes the C++ class, the C++ object, I should be more correct about this, and converts it into a tuple. And these functions are generally very simple. They're generally the simpler of the sort of 2 halves of the equation. So in this case, we see that, let me just read this to make sure I'm not leaving out any critical details. Right, so this function that we're writing, we call it convert, has to be a static function named convert on a struct or a class. This is just a requirement of how the Boost Python compile system is working. It expects to find a convert function that takes in a const reference to the thing you want to convert and spits back a Python object pointer. In this case, very, very simple. We extract the x and the y from the coordinate object. We use Boost Python make tuple to make a tuple. This is a good function to know about because it's very handy. It can make a Python tuple out of arbitrary C++ things. Here we then call PTR. So that we're calling PTR on a Boost Python object. And what this is doing is giving us the Py object pointer, the underlying Python object pointer. And we're going to increment its reference count. The reason we have to increment its reference count is because we've made a Boost Python tuple here. And that's really just a Boost Python object, which of course increments the reference count. And on destruction, decrements the reference count. So if we don't go underneath the covers here and bypass Boost Python to increment the reference count one more time, what will happen is when this tuple destructs, which it has to do on the exit from this function, Python will see that the reference count has gone to 0 and might reclaim it. So here we are, in some sense, artificially incrementing the reference count. Does that make sense? This is where we get into some of the stickiness of reference counting that Boost Python generally makes very smooth, but in this case, you have to kind of scratch your head a bit and think about how the gears are meshing. So the sum of all that is to say that when I return from this function, this tuple object has actually destructed its decrefed, the object, this pi object we're returning here, but because we have manually inc-refed it, the pi object coming out of here has a ref count of at least 1. It may be more depending on how your system is configured. So this convert function has to be a static member on a struct or a class. It has to be public. And that's it. They're often very simple. The 2 Python version is often very straightforward and simple because you have so much static type information coming from C++. You just know things will work. To register that converter, you use a template here called 2 Python converter. And it takes in the first template argument is the name of the class to be converted, and the second one is the name of the struct on which the convert function is defined. And you can call this you can invoke, you're actually constructing a little object here. You construct this inside your Boost Python module definition. So this typically gets registered at module import time. That's not required. You can actually register these anytime you want, but that's often the most convenient place to do it. If that makes very little sense, don't worry about it, because just remember, do this inside your Boost Python module definition, and you'll be fine. So the next thing, so what we've covered for type conversion so far is how to convert a C++ object into a Python object. It's one function, you register it, very simple, generally very straightforward. Now, if I want to convert the other way, there's 2 things that I have to do. One is create a function that takes a Python object and says, yes, it can, or no, it can't be converted to some specific C++ type. And that's because you could be getting all sorts of arbitrary things that try to come back across the boundary depending on how your code behaves. So what we have to do first is write our little checker function. Generally, it's called convertible. Kind of by convention, it's called convertible. It takes in a Pi object pointer, which is the low-level Python CAPI Pi object type. And what it's supposed to do is either return 0 if the conversion can't be done, or return the pointer itself if it can be done. So these can be pretty messy because you have to write this function so that it tests every possible angle, every possible sort of precondition, really, of the object you've received to see if it fits all the requirements. So here's what we're doing in this case. It makes sense in the end. First thing we do is we check, we call PyTuple check, and that's the Python CAPI function that says, is this thing a tuple of any sort? Is it a tuple? Irrespective of size or contents, is it a tuple? So if not, return 0. If so, we check, is it size 2? Because we require a size 2 tuple to convert into a coordinate because it only has 2 members. If it's not 2, we return 0. Otherwise, we check each of the elements in the tuple to see if they are numbers. That's actually a protocol defined in Python. And if both of those are numbers, then we return the object pointer. Otherwise, we return 0. So you can imagine how these become actually significantly more complicated if you have to go in and kind of introspect all the contents of some complex structure to see if it fits the model you're trying to build in C++. But this is the flavor of how they work. They're just, they're checking a lot of things to make sure all the I's are dotted and the T's are crossed. So the other half of the from Python conversion is the function that actually converts the function from a Python object to a C++ object. So typically you call this thing construct. And by the time construct is called, you know convertible has been called and convertible has said yes. So by the time you get to construct, you typically don't have to do any further checking. You can if you want, but it should be unnecessary. But the objects you get, the parameters you get to construct are a Pi object pointer, which is the thing that's already been passed through the convertible function. And you get this other thing of which we will not speak because it's basically sort of the transport mechanism for memory blocks and stuff. And I'll show you how to work with it. But I mean, it's called R value from Python stage 1 data. It's obviously like an implementation detail of what's going on here. So in this case, all we do is we extract the values from the tuple that we've been giving. We know it's a tuple. We put them into longs. The only real trick, the thing to see what's going on in here, is you use this invocation here to get a void pointer to some bytes that have been allocated for you. So Boost Python has said, okay, I know this can be converted into the thing that they want. I'm going to allocate the size of that class into this memory block here, and then I'm going to do in-place construction. So this may be the only time in your life that you see in-place construction used, but this is a place where it's used. So does everybody know what in-place construction is, more or less? You've got a memory block and you want to construct something directly in that memory block. It's a C++ism. You don't have to understand it to do this. Just remember this pattern. And then at the end, you say data convertible equals storage, and you're done. I don't know what this last line really does. I just know that it works. You could dredge into the details if you want, but there be dragons. Oh, sorry, yes. In the from Python. So, yeah. Well, if you miss it, so if my convertible function returns true when it shouldn't have, I'll get to this function to construct, and I'll start trying to grab data out of it, and I'll find that actually something fails along the way. That may result in exceptions. That may, depending on how defensively you code, that may result in seg faults. I mean, if you assume your convertible function is correct and it's not, and you just plow through the construct function, your construct function could delete your hard drive. I don't know, melt the core, whatever. It's it depends on how you've coded it up. But try to be very explicit and very correct, basically. Typically, you'll just get an exception. You'll get some kind of Python exception. Right. So again, remembering the details of this, not critical. Remembering the three moving parts, remembering kind of what needs to be done for type conversion is important. So finally, the last thing that you need to do is register the from Python converter, and that's done by pushing information onto this thing called the converter registry. And it has a function called pushback that takes the convertible function. This is the test function, takes the constructor function, which is the one that does the actual work, and it takes this boost Python type ID of the type that you want to be able to extract from Python. And this is using boost Python's RTTI magic to assign basically integers to different types. And it works. After you have done all these steps, you now have a system that allows you to transport arbitrary types back and forth across the Python C++ language boundary. And it's actually kind of awesome the first time you get it working. It's just you just like throwing objects back and forth between the languages and working with them, manipulating them. You kind of forget the fact that there's two languages involved. It's very, very cool. So it's worth trying this out at home, get a glass of wine or something and sit back one evening and to try to get this to work, and you'll feel enlightened a little bit, or you just think I'm an idiot because you get excited about things like this. Okay, you can try this out if you want on your own. Like I said, all the answers are in the workshop material, so you can kind of see a full explanation or a full solution. Yes? I don't think so. I know that in the past there wasn't, like 3 years ago there wasn't, because I had to write a whole set of boost preprocessor stuff to make an extensible system for that. They may have done that now. There's things keep happening in Boost Python that I don't always keep up with, but typically no. It's not Boost isn't some big hippie commune where everybody's always talking to everybody. There's sort of these silos, and so I don't think there's that kind of conversion going on automatically. But it's not difficult to do. It's pretty easy to automate, actually. So, right, this is a reasonably interesting topic. Does anybody care about this? Basically, I've written a C++ class. It's a virtual class. And I want to be able to subclass it in Python and override and implement the functions, the virtual functions in Python. This is a bit of an edge case, but I'm getting at least one nod here about how to do it. Okay, well, let's talk about it. It's interesting enough. But right, to set the stage again, I've got, in fact, ignore this. I mean, I've got a C++ class, virtual class, so abstract class, so it has some undefined functionality that has to get filled in by subclasses. And what we want to do is write that subclass in Python. And that's pretty cool, because now you're defining protocols and maybe defining frameworks and stuff in C++ that you can then fulfill in Python. That's kind of neat. The problem is, typically, Boost Python needs to be able to fully instantiate things before you can start subclassing them in Python. And because you have an abstract class, of course, you can't instantiate that, so what are you supposed to do? Well, the trick is they have this thing called wrapper, Boost Python wrapper, that sort of solves the problem. So if we look at this, we've got base. Base here is our abstract class. It's got some function f, it's undefined, and we have some function run base that takes an arbitrary base and calls f on it. And of course, what we want to be able to do is subclass base in Python and pass it into run base. Now, to accomplish that, we have to create this wrapper class. So here we see that one of its base classes is BP wrapper of base. Essentially, what wrapper does is implements the virtual functions and then routes Python calls in such a way, well, it's easier to show it. Okay, we see here base wrapper implements int f const, which is exactly the virtual function in base. So of course, base wrapper inherits from base. So base wrapper fulfills all of the virtual requirements, the abstract requirements of base. All it does, all this f implementation does, is route the call to this get override of f. Essentially, that's routing it to the Python function f defined on this class. So what we're going to expose, first we're going to expose run base, so we can call it from Python. That's just to demonstrate that this works. But here we're going to expose, using class underscore, we're going to expose the base wrapper class. Ignore the non-copyable. We can talk about that later. Tell Python that this class is actually called base. It's not called base wrapper. It's called base. Has an empty constructor and has this def f, which is the base wrapper f. Now, if I go into Python, this code here, I can import base wrapper and create a, which is a subclass of base, which, remember, is actually base wrapper. Is not, I mean, it ultimately is base as well, but it's really base wrapper in this case. Implement f, which just returns 42 times whatever's passed in, and I can call base wrapper run with an instance of a and pass in 5, and I get 210, which I assume is 42 times 5. Does that make sense? I mean, not have you memorized it, but does it sort of, do you see the dots that have to be connected to make this work? You have an abstract class, yeah.
The API is add and then you call run base. You have to different to extend your API. It's called like run base.
Yeah, I mean, the point here is that run base takes any base instance and calls f on it. And I wanted to show that that the f that ultimately is called is this f here, which is only defined in Python. That's the trick. Yeah. So it's a hard thing to describe until you actually have the problem yourself, and then it makes perfect sense. So just remember, if you ever want to override virtual functions in Python, you probably need to at least remember this, because you may have to use this. You don't always have to use it, but in the case of purely virtual functions, you probably do. You might have to still. To do any overriding in Python, purely in Python, you have to make sure the C++ knows to defer to that Python implementation. Yeah. So really the pure virtuality of it is irrelevant in some sense, but it makes it starker, I think, to see that. Try it yourself. Right, C++ exceptions. We have 30 minutes. Yeah, we'll go through this. We've talked a bit about exceptions and how you have these two different models. In C++, you have sort of native stack popping exceptions that kind of flow through your code. And in Python, they're really implemented at the C level as a bunch of registers that get set by functions that have failed in some way or have thrown an exception in some way. I don't want to equate exceptions with failure. By default, Boost Python, if it sees a C++ exception trying to get back into Python. So you've written your C++ module and exposed it to Python, and your C++ code throws an exception, and it's coming back up to Python. Boost Python will see that when it's coming across the boundary, and will turn that into a runtime error in Python land. So that's sort of the default behavior. As I mentioned, there are a few exception types, kind of memory allocation errors and things like that, that have automatic converters. By and large, though, runtime error is precisely what you get. So if I have defined my own exception, class exception here, and I have some function called throw exception, which, as you might expect, throws an exception, and then I expose that using def, what happens when I call throw exception is I see a runtime error. So yeah, very straightforward. It's easy to think about. It's very explicit, so Zen of Python kind of stuff at play here. What you'd like to do is to be able to, often at least, you want to be able to catch that runtime exception and do something with it. And that's very straightforward to do. You can do it in a couple of different ways. One way to do it is in the C++ code, have a wrapper around the function that might throw that catches a C++ exception and does the right thing, converts it into a Python exception. And that's what we've done here. So if we see we have void throw exception, which still just throws an exception. And then we have throw exception with translate. And this is a wrapper around throw exception. So if throw exception throws a my exception, I will catch that. I'll use this Python C API, the PyAir set string that I mentioned 3.5 hours ago, and tell it, please instead throw a system error with this string and then throw another C++ exception. This bears a little bit of discussion, I guess. So PyAir set string, what it does is fills in those 3 exception registers that I mentioned, the globals that Python uses to express exceptions. And then it throws another C++ exception. This C++ exception, it's the best way to describe all this. This informs the Python level. This informs Boost Python that something has happened down in the C++ level, and that it needs to look at the exception registers, which I've just set. And so what ultimately happens is Boost Python sees this and then throws this. I mean, another way of looking at it is this causes the stack to unwind all the way back up to Python, at which point Python sees this explicitly set exception, and your Python code just gets an exception, just a natural exception like you would normally deal with. I'm saying this a bit awkwardly, but it's kind of an awkward thing to explain. It's probably easier if you try this. If this is something you feel like you need to understand better, try it out. Just write this code, basically. Right, and so here we see now, if I call throw exception, because I exposed throw exception with translate and gave it the name throw exception, now I get a system error instead of the runtime error I was getting before. So the loop is complete. Right, and you can try this in the example if you want. And this is fairly well documented. There's a number of different ways to throw exceptions with the Python C API, but this is the simplest one, PyAir set string. An even simpler way to deal with this is that you can explicitly register exception handlers. You can tell Boost Python, anytime you see a C++ exception of this type, call this function. Call some function you can give it. So here's how that looks. Here we still have my exception, and we still have this function throw exception. And now I've got a function called translate my exception. And it takes as an argument a constant my exception reference, which we ignore. All we do when this function is call PyAir set string. Now, here's how we tell Boost Python what to do. We say register exception translator for the class, the C++ class, my exception. When you see my exception, call translate my exception, and then throw Boost Python error already set. So essentially, now we can expose throw exception naturally without having to write a wrapper, and any time my exception is thrown, this function gets invoked, and an exception is signaled naturally up to Python. The beauty of this is that if I have a whole family of functions, a whole bunch of functions that all might throw my exception, they're all automatically covered by this exception translator. This is the reason you would use it. It's a more scalable solution than writing wrappers for each of your functions. And it just works. There doesn't seem to be a system to go the other way, unfortunately. So if you get into an embedding situation where you have Python code flowing up into C++, it's not quite as easy, but it can be handled. Here we see the same exact output. We get a system error instead of a runtime error. Great. So, okay, right, call policies. Are exceptions clear to everybody? Call policies are interesting, but I want to make sure the exceptions, at least, it isn't just like, I know we're late into the day and late into the workshop. Call policies are going to be a bit of a mind twist. So let's step way back. C++, of course, allows you to do all sorts of wacky things that Python simply cannot do. Things like maintaining internal references to objects that no longer exist. In Python, in C++, it's really easy to do. In Python, it's effectively impossible because of how reference counting works. So to mediate that difference, to mediate that friction, you need to sometimes tell Boost Python about non-explicit relationships between things. So for instance, if I have a function that takes in a class and returns a pointer to something inside that class, Boost Python doesn't really know that. It doesn't know about that relationship. And so it might legitimately allow you to delete the thing the external reference and not know that the pointer you returned, the reference you returned, actually relies on the existence of that outside thing. You'd like to be able to tell it, don't let this thing die until this pointer is no longer in use. And that's effectively what call policies are for. They're a way to communicate to Boost Python these kinds of relationships between objects. So let's, yeah, there's a triad here, but we won't get into that. But let me see if I have enough code to make this completely clear. Well, okay, I don't really, without bringing up code, which I think is just sort of beyond all of us at this point. The point is that if I have a function that takes in this matrix, an instance of matrix here, and returns a row object, which is just some wrapper that manages access to a particular row of data in this matrix, and I expose that from C++ into Python, Python doesn't know that the row relies on the existence of that data that's managed by matrix. All it knows is it's got two Python objects that have no relationship as far as it can see. There's no references between them. And so it might let the matrix thing die. A matrix might get garbage collected while row is still alive, but row will start to fail because, of course, it's now pointing at deallocated memory. Right? So this is the kind of overarching archetypal reason for having call policies. They allow you to tell Boost Python, hey, don't let matrix die. Keep it alive secretly for me. Give it an extra ref count until row goes away. And the terms you'll hear used are custodian and ward. In this case, when I give this talk to foreign audiences, I sometimes have to explain those terms. But okay, so custodian and ward. The custodian is in charge of the ward. So row is the custodian, matrix is the ward. And as soon as row goes away, everything is allowed to go away. But as long as row is in existence, matrix has to be kept in existence. So how do I express that relationship? It's right down here. I should have just stuck with the matrix and row terms, but basically you specify a call policy as the last argument, or the third argument, I should say, to a def call. It can be member functions or free functions, I believe. And a custodian and ward relationship looks something like this. So here we have a function called foo that takes a reference to an external class, and what's going on here? Yeah, maybe it returns, it does something to an internal ref. I don't remember. So I apologize about that. But you specify the relationship using these various call policies as the third argument. And the arguments, the template arguments to your custodian and ward example here are typically indexes into the cardinality of the arguments for the function that's being managed. A lot of words. Basically, it's saying this is telling Boost Python that the custodian in this case is the second argument, internal ref, and the ward is the first argument, in this case, external class. Don't worry if this doesn't make complete sense right now. It will make sense when and if you reach a point where it actually matters for your code. This typically is not, I've had to use this in production code maybe twice in something like 10 years. So it's not very common, but it does come up. And when you run into this wall, when you run into this situation, it'd be good to know about it. But just remember that it's there, call policies. You can chain call policies, kind of chain them by embedding them inside one another. So you can have very, very sophisticated relationships can be expressed between the various things because, of course, you can do arbitrarily ridiculous things in C++. Here's a list of all the call policies if you want some light bedtime reading. Okay, yeah. So call policies, step back again, call policies are there so that you can tell Boost Python about relationships between C++ objects that it would not otherwise know about and that it needs to know about to prevent seg faults. That's the big reason that it exists. And you can try to use it. Well, look at that. Okay, that's it. Yeah. So are there any questions? I mean, high level, low level details, any questions at all? We got about 15 minutes, and I'm willing to stay beyond that. I mean, you can leave anytime you want, but yes. Yeah, there was a question about that earlier in one of the breaks. I'm fairly certain that it has a set of APIs kind of tacked onto the side. It's like Boost Python Numeric or something like that provides a friendly API on top of it. But it's something I have almost no experience with. I just kind of know that it exists. You might search on that in Boost Python Numeric or Boost Python, I think it's Numeric, but something out there does exist. and it's also not too hard to write your own if you need something more specific. Yeah. Yes. Okay. Mhm. Okay. Okay. Yeah. Yeah. Talk to her. Yeah.
So now, since you made a C extension,
Mm-hmm.
the boost, how am I going to package and distribute that?
Well, that's a good question. It's not as simple as distributing, of course, pure Python code, because now when somebody gets it, they have to compile it for their own system, or you have to give them a pre-built version. One of the big downsides, and you've hit it on the head, one of the big downsides to using compiled extensions, is that, especially compiled C++ extensions, are that you've bought into the entire world of compiler flags, different variations of Python, Python versions, all this stuff you often don't have to deal with. So sometimes you can use setup.py sometimes. You can distribute them as things with make files. You can distribute them as just a bunch of code and tell them, enjoy. But I guess the silver lining in some sense is that typically the bindings are not all that complex. They're small bodies of code. So you've got some big C++ library over here. It's 20 million lines and it's the lifeblood of your company. You've got some Python script that needs to call this part of it. So you just expose just that part of it. So it's a relatively simple thing to compile often. But making them available for public use, like in an open source project, can be significantly complex. Now, perhaps CMake has good solutions for this, because he built a...
The team just set up tools like 5.3 or 5.4 now, and they use like initiatives to build stuff, but that doesn't really work. Visual Studio is like painful. And but CMake is very good at like generating the native like makefile, Visual Solution file, the makefile, the ninja file, or whatever. One option would be to, when you do like C extension, you keep the tool, but to drive CMake. CMake would be a requirement for in the context of like extension that set the tools.
Okay.
It's something we are discussing like, with the other guys.
Yeah. It's not easy, but yeah, it can be done. Yeah. I'm not sure I understand that. Oh, to ship just the slice of Boost that is Boost Python? I don't know, but I'm it does rely on the shared pointer and a whole bunch of other bits and pieces, MPL and things like that. Yeah. Yeah. I mean, yeah. Boost Python is compiled. There's a boost python.so. Yeah. And it depends on one of the biggest sticking points that people run into is that that library, boost python.so, depends very much on the version of libpython.so that you're using. And mismatches between those that's a real source of pain in some build systems. Yeah.
With the Boost, they have like very good support for like CMake. And like I rewrote the build for the exercise today, and I put an issue on the tracker, on the GitHub tracker with a reference, and you find package Boost, and then you can very easily build like your code, put it on like
Yeah, I'm excited to look at that. I've never really worked with CMake, so this will be an interesting introduction. Yeah. Okay, well, yeah, thanks for attending. If you have questions later on, you want to talk about stuff, specific topics or whatever, or you want to just grab me when my brain is not quite so frazzled, that would be, I'm always happy to talk about this stuff. Yeah. A Python equivalent to call policies. I guess not. I mean, that's really a bunch of template magic to to make C++ work with Python and not the other way around. But if you have a specific question or like use case, maybe, okay, yeah. Okay, well, thanks. Thanks.